Today's lesson is about polynomial functions, mainly the ideas of graphing polynomial functions. Some are easier than others, and we're kind of going to run the gamut of all of them. So generally, your polynomial function is a function of this form, where these a sub n terms, a sub n minus 1, all the way down to this a sub 1, a sub 0, those are your coefficients. Those are just going to be numbers. And then you have these x to a power. And usually you start with the highest power here. We'll call that n, whatever the n power. Then the next one down would be 1 less than that, and 1 less than that. And you continue all the way down till you have a first power and even the 0 power. And normally we don't write 0 power, so like this one you wouldn't write 0 power because that would just be 1. You would just write a sub 0, and this is your constant term. So this is what your typical polynomial function would look like, and this is the general form of a polynomial function. So what we need to do is look at some characteristics of the graph. So whenever you're graphing a polynomial function, you should know what it's going to look like before you start. Well, some things that happen with polynomial graphs is that they're all continuous. Continuous means that you're going to graph this function with no breaks, no holes, no gaps. So you should be able to draw the entire graph from start to finish without taking your pencil off the paper. So this example here would be the graph of a polynomial function. I could draw that entire graph. It has no holes, no breaks, no gaps. I can draw that whole graph without taking my pencil off the paper. This one over here is never going to be the graph of a polynomial function, right? Because the only way I can get from one piece to the other would be to pick my pencil up. And it's got this break in it, this gap. So this is never what a polynomial function is going to look like. This one is more along the lines of what some polynomial functions look like. Not every one will look exactly like that, but they will all be continuous. So then the next thing that happens with polynomial graphs is that they have what we call smooth turns. In that case, you're not going to get any sharp points when you put your graph together. Now, when we put our graphs together, they're going to be segmented because we're going to put them together in pieces, so they're not going to look great, but in the end we need to smooth it out. So if you look at this graph right here, it's got a bunch of turns to it, okay? And where the graph makes that turn, where it goes up and then goes down, we call that a turning point, which we'll talk about in a little bit. But every one of these turning points, that's a turning point, this one right here is a turning point, this one right here is a turning point, here's another turning point. They should be smooth turns. Now some are going to be sharper than others, but each one should be a nice smooth turn. Okay? This is not the graph of a polynomial function. That's your graph of your absolute value function, which you should be familiar with. It has that V shape to it, but it comes to a sharp point right here, in that it doesn't have this bend to it like, say, a parabola would have a bend to it. It has one line, it comes to a point, and then has another line this way. So this is not going to be the graph of a polynomial function. We will never have those sharp points. You'll never have a polynomial function go like this, and then bounce like this, and then bounce like... That's never going to happen. This should never have these points. If anything, it should go like this, and turn, and turn, and turn, and turn, and turn, and so on. Again, some terms might be sharper than others, but it should never come to a sharp point. So the two polynomial function types of polynomial functions we look at first are the simplest, and they're called our power functions. Our power functions are any function of this form, f of x equals x to a power. Now that power has to be a whole power, a positive whole number power. You know, if it's a negative power, you know for algebra how that works. If it's a fractional power, again, algebra, you know how that works. So really it's x to a power, but that power right there, that n, has to be a positive whole number, either even or odd. So the idea is we break these into two groups, the even power and the odd powers. All the even powers look the same, all the odd powers look the same. So x squared, x to the fourth, or x cubed, x to the fifth, they're in two categories. So all your even powers look like the parabola x squared. If you look at this gray line here, This gray line here is my, which I'm now making red, is my x squared, and I'm going to really junk that up. So let's just look at this x squared here, the gray one. If you follow the curve, okay, it's got that parabola shape, which you should be very familiar with. If I draw any other even power, so here's an x to the fourth. X to the fourth has that same parabola shape, so if you follow it, it still has that same parabola shape as you work your way down. But there's a slightly different curve to it, but it still has the U shape to it. And what happens is, as the power increases, if you look at what happens between -1 and 1 versus what happens after 1 and after -1, as far as the graph goes, in here, right, in here between -1 and 1, my graph looks like it's sagging in towards the x-axis more, okay? And as the power increases, that's going to happen more and more and more. It's going to sag in closer and closer to the x-axis. But after 1 and this way on -1, what happens is the graph doesn't sag in more. It's not like it's going to continue sagging out like this. What happens is that the graph increases faster. It shoots up at that point. So this point 1, 1 is kind of that changeover point. So it sags in here and then it shoots up after that. And that's going to happen. The bigger the power, the more that's going to have. So if I did say like an x to the 6th, right? It's going to sag in more in here. Right? It never really goes horizontal, but you know, we can't zoom in too well on this, so it's going to look kind of horizontal. And then after this, it's going to shoot up faster and shoot up faster. But if you look at it, it still has that U shape to it. And all even powers are going to have that U shape to them. And generally the same thing is going to happen here with the odd powers, right? If you look at this light gray one here, this is my light gray graph. It's your cube graph, and you should be familiar with the shape of a cube. Now look at the 5th power. Between -1 and 1, it sags in closer to the x-axis on either side, okay? But then after that point, it shoots up faster, and here it shoots down faster and increases faster. And that's just because that's what powers do. For any number between 0 and 1, when I raise it to a higher and higher power, it gets smaller. Like if I go, okay, 1/2 to the 2nd power versus 1/2 to the 4th power. I've raised it to a higher power, but the answer I get is actually smaller, right? This is smaller than this. So any number in here that I raise to a higher power, the y value or the answer gets smaller, which makes it sag in closer. But any number bigger than 1, like 2 to the 2nd or 2 to the 4th, my answer gets bigger. If it gets bigger, it's going to shoot up faster. Well, that's sort of just the idea of powers, but these are what our power functions look like. Even powers all look like the even ones, and odd powers all have this odd power shape to them. The power being bigger and bigger and bigger just sort of alters that curve a little bit more, but generally they have the same shape. Evens, same. Odds, same. Now one thing you should be familiar with is sort of then transforming these graphs. These transformations are the idea of, you know, taking your graph and placing it in a different location, altering the function, and how does that alter the graph. So we could reflect the graph, we could stretch or shrink the graph vertically, we can shift the graph horizontally, we can shift the graph vertically. It all depends on how you change the function. So let's look at reflections first. So say I'm just dealing with a general function, y equals f of x, and then I want to start changing that function through a transformation. Well, if I reflect it, it depends on where that negative is. If I have a negative inside my function or outside my function, and it's a multiple. So if I multiply by a negative outside my function, the first one is going to reflect in the x-axis. So you're going to flip the graph over the x-axis. If I have a negative inside my function, I'm going to reflect it over the y-axis. And this one can get a little tricky, so we'll have to do an example of that, and I'll show you something that can occur there. As far as stretching and shrinking your graph, it's all about this multiplier out in front. Okay, you have that multiplier out in front, and you want to say, all right, well, what does that multiplier do? Well, if it's negative, back to number 1, it's going to reflect it over the x-axis. So let's remove the sign from this a number in front of f of x. Okay? If I remove the sign in front of for this number a, I'm really taking the absolute value of it. So if I look at a, if the absolute value of a is less than 1, it's going to shrink my graph vertically. However, if the absolute value of a is greater than 1, it's going to stretch my graph out vertically. Okay? And what that basically means is a stretch, my graph's going to look skinnier. And a shrink in the vertical direction is going to make my graph look wider. Okay? So that's all based off of this. If I have the absolute value of a is less than 1 or greater than 1, okay, I have one of these two things. But that's that multiplier out in front here. Alright, then the other things we can do is we can start shifting our graph. So if I want to shift my graph horizontally or vertically, I'm going to add or subtract some value somewhere on the function. These two I'm adding and subtracting inside the function. These I'm adding and subtracting outside the function. That's the key here. Is, see, these two here are inside the parentheses. These two are outside of the function, outside the parentheses. If I add or subtract inside the function, it's a horizontal shift, and that's based off of c. You know, if I subtract c, I move to the right. If I add c, I move to the left. And here, if I add or subtract outside, I do a vertical shift. So I do downward if I subtract d, and upward if I add d. So a very simple one that you might be familiar with would be if I gave you this. F of x equals x squared, right? You know that that graph looks like this. And that's just a polynomial, right? It's a very simple polynomial, just one term, x to the second. That's a polynomial, so the graph should be one solid piece, and it should not have any sharp points. It should have all smooth curves. That's what I did. But what about this function? G of x equals x minus 2 squared plus 3. Well, it's still a square, okay? If you look at that, it's still a square. So it should still have the same shape that the other one has, but then I made these changes. I have a minus 2 inside and a plus 3 outside. This is going to make me move to the right, and this one's going to make me move up. So if I take my parabola and I move it right 2 and up 3, right 2 and up 3, this is where my parabola is going to be in terms of this vertex point. So I go right 2, up 3, I'm located here. I draw my graph, and that's what my parabola should look like. Now that's not the greatest graph at all, but it gets you the idea of where my graph is located. It's located at this point 2, 3. Okay? And it goes a U shape from there. So here's a couple more. Alright, let's do A. F of x equals negative x to the 7th. So odd power and a negative out in front. So what do those two things do? Odd power gives you the odd shape, and the negative out in front is going to flip it over the y. It's going to flip it over the x-axis. So your typical odd power will look like this. Now if I flip that over the x-axis, this is going to flip down, this is going to flip up. Everything's going to flip. So what I get is my new graph is going to look like this. So that red picture is really the graph of this function. And whenever you're going to have to graph any of these, you only want to see the final picture. I'm showing you the intermediate step just so you can kind of see where it starts and where it ends. Let's go to the next one. F of x equals negative x plus 2 to the 4th. So now I got a couple of things. 4th power, even power. So that tells you the shape. Plus 2 inside and a minus outside. Two things happening. Shift and a flip. Whenever it comes to these, you should always flip first, move second. Okay, so if I flip first, this is going to be flip over the x-axis, and this is going to move me to the left 2 spaces. Okay, so if I look at this and go, alright, well, I got this parabola. Okay, here's my parabola. This is my y-axis, this is my x-axis. I have this parabola. So I'm going to look at the even power, so that's a parabola. I'm going to move it to the over the x-axis. If I flip first, I move it over the x-axis. That's going to put it here. Right? And then I'm going to move it left 2 units. So that's going to put my final picture here. Okay? So that yellow picture is the final result for this function. Okay? And just something just to remember when you're doing these is that when you move horizontally, which is what's happening inside the graph, okay, it's always kind of the opposite of what you think is going to happen. Like you see this +2, you think +2 I should move to the right, but that +2 actually moves it to the left. When you do the horizontal movement, it moves it differently. If you're not sure, look at this point, right? If I moved it 2 units to the left, that point is -2, 0. The best way to check this is to take this -2, plug it into the function, and make sure you get this 0 out of it. So if I plug -2 in here for x, -2 plus 2 gives me 0. 0 to the 4th is still 0. 0 times -1 is still 0. So if I plug this -2 in, I get 0 out. That's the best way to check it, because if I moved it the other way, and I did it the wrong way, I'd be at this point 2, 0. If I plug 2 into this function, I don't get 0, so I would have known that was wrong. Alright, let's do one more. Let's make some room here. Okay. So if I do one more, if I look at this one, x minus 3 to the 5th plus 4. So the 5th power means it's an odd power, odd shape. -3 inside plus 4 outside. These are the things you need to watch out for. So shape is odd. Okay? -3 inside moves it to the right. Plus 4 outside moves it up. So I do my odd shape, which is this. I'm going to move it right 3 and up 4. So I'm now located here. So if I draw my graph, it should be my odd shape through that point right there. And check it. I plug 3, 4 in. So if I plug 3 in to the function, do I get 4? Yes. 3 minus 3 is 0, to the 5th is 0, plus 4 is 4. So I moved it in the right location. Okay? This idea of transformation should not be a new concept, and it's something we're going to use a lot as we move through the semester when it comes to graphing certain types of functions. Alright, let me give you one more example just so you see it, because it's the one tricky one. Alright, let's erase some of this. Alright, so if we give you one where there's a negative, sometimes the issues with the negatives come into play. And whenever you see a negative in a horizontal transformation, you have some issues. So let me give you this function. How about f of x equals -x plus 2 to the 3rd. Okay? And you have to graph this. Now there's two things that are happening here. That's the tricky part. The negative inside and the horizontal shift. The power is telling you the shape, and that's fine. Odd power, odd shape. But when you see something like this, you got to think about this function differently. Whenever you have a negative inside a function, doesn't matter what kind of function it is, a negative inside a function, the whole interior of the function should be multiplied by a negative, not just the x. And that's the problem with the way we're seeing this. So if I write it this way, negative x minus 2 to the 3rd. If I distribute this negative in, it's still -x and a plus 2, but now my entire inside of my function is multiplied by a negative. That's the way I need to see it. So what is this? Negative inside, I have to flip over the y. And this -2 inside means I have to move to the right. And the problem is, if I look at it this way, I'll see this plus 2, and I'll probably move it to the left, which is the wrong way to do it. It should not be moved to the left. So if I put my graph together, I have an odd shape, Now I have to flip that over the y-axis. So anything on one side comes to the other and vice versa. So this is my flip over my y-axis. And then I have to move it right 2. So this point right here goes right 2 units. So now it's here at 2, 0. My graph should look like this. Okay. Now if I'm not sure if that's right, look at this point, 2, 0. If I plug it into the function for x, 2 minus 2 is 0 times negative is 0 to the third power is still 0. It doesn't matter where I plug it. I can plug it into this one because they're the same. I plug a 2 in, negative 2 plus 2 is 0 to the third is still 0. So I moved it in the right location. If I was over here 2 units and I moved to the left like I shouldn't have, I'd be at negative 2, 0, and if I plug this x value in, I won't get that y value. So you see that graphing power functions is fairly easy if you understand the idea of transformations. You have two shapes to pick from. You have a series of transformations you make to that shape and you draw your graph. Now, not every polynomial function is a power function. I mean, the idea with the power function is it has to have a certain form. However, if we have that long form polynomial that I showed you initially, which was that f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus and so on all the way down to a sub 1 x plus a sub 0. If I have a polynomial in this long form, remember a sub n minus 1, a sub 1, a sub 0, these are just going to be numbers. You have these x to a powers. These are going to be much more difficult to graph, so we have to look at these in a little bit more detail. So the major thing that comes up with graphing these is this concept of zeros. Okay, zeros of a polynomial. If I'm looking at zeros of a polynomial, right, I need to know what a zero is, and then we'll learn how zeros affect the graph. Well, if you think about one thing is what is a zero of a function? Not just a polynomial, but any function. A zero of a function is any place where that function would be equal to 0, which makes sense in terms of the name. Another word for zeros are roots. Sometimes you'll see it roots of a function or zeros of a function. But it's all the x values that make the function equal to 0. So if I'm trying to find the zeros, I can try and solve this particular equation, f of x equals 0. Now, let's look at some things in how zeros and graphically how functions are related. One, looking at the degree of a function. The degree of a function is fairly important. The degree of a function is the highest power of that function, in terms of a polynomial at least. So if you look at this particular long form polynomial that I wrote down here, n is the highest power because each power after that is less than it. Here's n minus 1, the next one will be n minus 2, n minus 3, all the way down to a to the first, and then, or sorry, x to the first, and then x to the 0, which we don't write. So the degree is the highest power on the variable for this polynomial. So a couple of things that happen. If you look at the degree of the function, the degree can tell you two things. It tells you about turning points and tells you about the number of zeros you could get, which also relates to something called x-intercepts, which you should already be familiar with. So one, if the degree of your polynomial is n, okay, then your polynomial's graph should have at most, and that's a key word, keywords, at most n minus 1 turning points. Okay? Now a turning point is where your graph changes from going up to going down. So this right here would be a turning point, this right here would be a turning point. Okay? So we can also call these relative maximums or relative minimums. Okay? But right now we'll just call them turning points. This says that your graph will have at most, okay, if I erase all this, your graph will have at most n minus 1 turning points. Okay? So that's the max. Now that most means that you're not going to have more than it, but you could have less than it. Here's another kind of trick to that, which, you know, it's not stated anywhere, but it just works out, is that if n minus 1 is even, okay, so if n minus 1 is even, you would have at most that even number of turning points, but you could have less than it. If you're going to have less than it, it should still be an even number. So if I look at this, say f of x equals 6x to the 5th plus 3x to the 4th plus 5x cubed plus 2x plus 1. Here is my polynomial function. The degree is 5. The maximum number of turning points is going to be 5 minus 1, or 4. Okay? Now that's an even number. That's the maximum number of turning points I'm going to have. If I'm going to have less turning points than this, because that's only the max I can have, it should still be an even amount. So that means I'm either going to have 4 or 2 or none. These are the only even numbers that are 4 or less. That's the number of turning points I could have. Those are the only options. If this is an even number, it's got to stay even if it's going to be less. And these are the only even numbers less than 4. So I either have 4 turning points, 2 turning points, or no turning points. I'll give you another one. If I give you f of x equals negative 2x to the 8th plus 3x to the 5th plus 2x squared plus 1. Okay, the degree of this is equal to 8. Okay, that's the highest power on the variable. So then the max number of turning points is going to be 1 less than that, which is 7. So now this is an odd number. Now I could have less turning points than 7, but since 7 is odd, the only odd numbers less than 7 will be 5, 3, and 1. So the only number of turning points I could have if I don't have 7 would be 5, 3, or 1. So if it's odd, it stays odd. If it's even, it stays even. But this is the maximum number of turning points you can get. And this is the only other option for the number of turning points you could get for this function. Alright, your graph also is based off of the degree in terms of the number of zeros. If you look at this, number 2, the graph of f of x has at most n real zeros. Now that at most comes into play again. At most n real zeros. So the maximum number of zeros you can get is based off of the degree. So the degree is 8. The maximum number of turning points I get is 8 minus 1, which is 7. And the maximum number of zeros would be 8 itself. Okay, is the degree. The degree is the maximum number of turning points. 1 less than the degree is the degree itself is the maximum number of zeros, and 1 less than the degree is the maximum number of turning points. Okay, and zeros have a lot to do with x-intercepts. If something is a 0, it's an x-intercept for the function. So not only is this the maximum number of zeros you can get, but this is also the maximum number of x-intercepts that you're going to get. And that's what leads us to the next thing, is when you talk about zeros of a polynomial, if something is a 0 of a polynomial, okay, if a is a 0 of some function, then there's 3 other things that are also equivalent statements. One is that x equals a is a solution to this equation f of x equals 0, which we've already talked about. I mean, that's the definition of just what a 0 is. The 0 is any value that you could plug in for x that would make the function equal to 0. But these two, these next two, here and here, are ones that often people don't realize. One is that if some value a is considered to be a 0 or a solution to this equation f of x equals 0, then that means x minus a had to have been a factor of this function. That's going to be a pretty key one when we're going into the idea of factoring to help us find x-intercepts. Also, if a is a 0, then a comma 0, that point, a comma 0, is an x-intercept for the graph of the function. And that's the key graphically of what zeros mean for the graph. That's why zeros are so important. When we're trying to put a graph together, we're finding zeros, we're actually finding the x-intercepts, which really defines sort of the central location for the graph itself. So these four statements all mean the same thing. Zeros are solutions to this equation. Zeros are factors in the form x minus that 0. And also, the zeros are x-intercepts for the graph of the function. So if I give you an example where you have to find the real zeros for a particular function. Now, as far as real zeros versus zeros go, there are two types of numbers, really. Real numbers and imaginary numbers, what we call complex numbers. We're going to only look at real numbers. We're not going to look at imaginary numbers. Imaginary numbers deal with the square root of -1 being equal to I. You may have seen that, maybe you've never seen it before. We're not going to deal with imaginary numbers at all because graphically they have nothing to do with graphing our polynomial functions, so we're going to just ignore these imaginary numbers. So when I say find the real zeros, I'm really just asking you to find the ones that don't include the imaginary ones. If we said just find the zeros for a function, technically that question means you can also include the imaginary zeros, but again, we're going to just ignore imaginary zeros. So if I'm trying to find the zeros for this function, I could word this question a little bit differently that says find the x-intercepts for this function, and it would be the same exact question, worded a little differently, but zeros and x-intercepts are the same thing. So what I have to do is I have to solve the equation f of x equals 0, right? I have to figure out when is the function equal to 0. So I have to take x cubed minus x squared minus x plus 1 and set it equal to 0, and I have to solve that equation. It's a polynomial equation. The primary way you solve polynomial equations is by factoring. So I have to be able to factor this polynomial, and this is going to be a huge part of what we do throughout this whole section. So if I have to factor this, there's lots of ways you've learned to factor in algebra. The main way that I'm going to factor this is by grouping. So I look at this and say, okay, I'll group these together, I'll group these together. I'll pull out an x squared, and I'm left with x minus 1. If I pull a -1 out of these two, I'm left with an x minus 1. The key to factor by grouping is that you get a second factor in common. So if I pull that second factor in common out, I'm left with a x squared minus 1. Well, x squared minus 1 can be factored even more, so I get x minus 1, x minus 1, x plus 1 equals 0, which I can actually write as x minus 1 squared times x plus 1 equals 0. It doesn't matter either way you write it, but I could write it that way, which tells me that either x minus 1 equals 0 or x plus 1 equals 0. So I get x equals 1 and x equals -1. So these are my solutions to this equation here, but these are also my zeros for the polynomial. They're also my x-intercepts for the graph of the polynomial. Okay? And look, 1 is a 0. X minus 1 was a factor. -1 was a 0. X plus 1, which is actually, if you look at it, x minus -1. Right? So anytime you have a 0, x minus that number is a factor. Here's a 0, x minus that number is a factor. Here's a 0, x minus that number is a factor. So those four statements I had earlier are all the same, and you can see how they're the same with this example. Here's another one. Find the x-intercepts for the graph of f of x. Okay? So if I look at this function, I got to find the x-intercepts. I got to find the zeros. I have to solve f of x equals 0. So that would be negative 2x to the fourth plus 2x squared equals 0. Well, again, it's a polynomial equation. Primary method of solving polynomial equations is to factor. So think about all the things you learned in algebra for factoring. First thing you should look for is there a common factor between all the terms? Here, yes. I'm going to pull out a negative 2x squared. So I pull a negative 2x squared, I'm left with an x squared. And here I'm left with a negative 1. The reason I pulled out a negative is so that this was easier to factor later. So what do I have? I have negative 2x squared times x plus 1 times x minus 1 equals 0. So that means either negative 2x squared equals 0, x plus 1 equals 0, or x minus 1 equals 0. So x equals 0, x equals negative 1, x equals positive 1. I have 3 zeros. What was the degree of this polynomial? 4. So if the degree is 4, the max number of zeros was going to be 4. But I could have less than that. And what did I get? 3. So it still follows. And in a way, you can think of it that I got 4 zeros. Because I got this 0 from this factor. I got this 0 from this factor. And this factor right here is really 2 factors in one. There's an x and another x. Which means one could be equal to 0 or the other one could be equal to 0. And essentially there's 2 solutions there. They're just repeated. It's the same solution twice. It's like if I had x plus 1 squared, right? There's an x plus 1 and another x plus 1. So if this one would get me x equals negative 1, this one would give me x equals negative 1. It's a repeated solution. So, I mean, that has nothing to do with this problem, but that's just an idea of a repeated solution, right? You think of it as one solution, but it's really, you think of it as two solutions, 2 of the same solution. So in a way, I did get 4 zeros. I got 3 distinct zeros, but 4 zeros total. The second part of this question, find the possible number of turning points. Well, if the degree is 4, the max number of turning points has to be equal to 4 minus 1, which is 3. So that's the maximum number of turning points. As far as the possible number of turning points I could have would be 3 or 1. Because if this is odd, if it's less than it has to be odd. Now that's not the case for the zeros. Zeros could be any number less than the max number. But for turning points, if this is odd and it's less than it has to still be odd. Finding the zeros is one component of graphing a polynomial function, but another major component of graphing a polynomial function is the concept of the leading coefficient test. Now the leading coefficient test has to do with the ends of the graph. What happens at the far left hand and far right hand endpoint of the graph. Now, as x moves to the left and to the right without bound, meaning all the way from negative infinity on this end and positive infinity on the other end, okay? That's the ends of the graph. As x moves to the ends of the graph, okay? What happens to the graph is based off of this thing called the leading coefficient test. Now, in the leading coefficient test, there are 2 components that you look at. Here's a general form polynomial. So when you look at this general form polynomial, we talked about the degree, and the degree is this highest power. But there's also something called the leading coefficient, and the leading coefficient is the coefficient in front of that highest power variable, in this case a sub n. I'm going to look at these 2 things, and this is going to determine what happens at the ends of the graph. So if the degree is even or odd, and if that leading coefficient is greater than 0 or less than 0, I'm going to determine what happens at my graph. So I need two things, the leading coefficient and the degree. So this is called the leading coefficient test, but you don't primarily just look at the leading coefficient. You also need to talk about the power as well. So if my leading coefficient is positive and my degree is even, both ends of my graph should point upward. So as x goes to negative infinity, which is on this end, I should be pointing upward, and as x goes to positive infinity on this end, my graph should be pointing upward. Another way to state this exact same thing, I mean this, when I do this, is the same thing as saying as x goes to negative infinity, that's really the left hand side, y is going to positive infinity, y is going up. And as x goes to positive infinity, that's the right hand side of the graph, y is also going up, so y is going to positive infinity. So this picture here really is stated this way in more concrete terms. Okay? So let's look at another one. How about when my leading coefficient is negative and my power is even? Then I have this shape to the ends of my graph. So if I think about what that is as on the far left hand side my graph is pointing down, and on the far right hand side my graph is pointing down. So this picture here means as x goes to negative infinity, that's the left hand side, y is pointing down, so y is going to negative infinity. And as x goes to positive infinity, that's the right hand side, y is going to negative infinity, y is pointing down. This means essentially when y goes to negative infinity, means y is pointing downward. So this means the left hand side of the graph, this means the right hand side of the graph. This is talking about the direction in which that graph is pointing. Okay, so let's look at the next one. Odd powers. So when we do odd powers, if my power is odd and my coefficient is positive, I have this shape. So if my shape is down and up, on the far left my graph will be pointing downward, and on the far right my graph will be pointing upward. That's if I have an odd power and a positive coefficient. So I could read this as x goes to negative infinity, that's the left, y is going to negative infinity, that means it's pointing down on the left, and as x goes to positive infinity, y goes to positive infinity, that means it's pointing up on the right. Last one, if my power, my degree, is odd, okay, but my coefficient is negative, I'll have this shape to the ends of my graph, which means on the left I point up and on the right I point down. So on the left is as x goes to negative infinity, I'm pointing up, so that means y is going to positive infinity. And as x goes to positive infinity, y is pointing down, so y is going to negative infinity. Okay? So this leading coefficient test determines that whole huge chunk of the graph, the ends of the graph, just purely by looking at the degree and looking at the leading coefficient. So let's do these two examples I have here. One thing to understand about the leading coefficient test is that it only determines the ends of the graph. What happens at the ends of the graph. That's it. But that's a huge chunk of the graph. So for this example, f of x equals negative x to the fourth plus 7x cubed minus 14x minus 9. The key is this negative x to the fourth. This is your degree, this is your leading coefficient. So I have an even degree and I have a negative coefficient. So this is the behavior at the ends of my graph. Now what happens in the middle, we don't know, but at the ends, this is what's going to happen. So as x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, y goes to negative infinity still. This is the left-hand side of the graph, and it's pointing down. The left-hand side of the graph, and it's still pointing. Right-hand side of the graph, and it's pointing down. Okay? Do another one. So g of x, 5x to the 5th, 2x cubed minus 14x squared plus 6x. The key to this is 5x to the 5th. This is my degree, this is my leading coefficient. So if I look at what I'm dealing with here, I have an odd power and a positive coefficient. So this is the picture I should have on the ends of the graph. So if I think about that, I should be on the left, x goes to negative infinity, y goes to negative infinity. Okay, and as x goes to positive infinity, y goes to positive infinity. On the left, my graph goes down. On the right, my graph goes up. Okay? And that's how you read that. This is a really nice thing to do when it comes to graphing polynomials because it doesn't take much work. You got to know the table, but it doesn't take much work to get your answer. And the ends of the graph are really half of your graph done with a little bit of computation. Now what we need to do is put this all together to draw the graph of a polynomial function. If I have a polynomial function in this form, f of x equals x plus 3 to the 4th plus 2, I don't have to follow these steps I have laid out because this is just one of those translation polynomial functions in that it's an even power. I have it left 3 up 2. However, if I have a polynomial in long form, not in translation form, but in long form, say like this example here, I can't just say, oh, let's look at the power, let's move it left, let's move it right, let's move it up. So this is when I would follow these steps. So the 4 steps you need to follow. You could do this in more steps, but I think less steps is better, and these are sort of the steps I like to follow. First, apply the leading coefficient test. We just talked about that. Abbreviated LCT. Okay, so apply the LCT. 2, find your intercepts. Okay, x-intercepts means find the zeros. Solve the equation f of x equals 0. You could also find your y-intercepts. It's fairly easy to do, so that's why we include this in here, and it gives us a little bit more detail on our graph. You find your y-intercepts by letting x equal 0, or essentially finding f of 0. Once you do that, you're going to start putting your graph together from those first 2 steps. You're going to have some gaps in your graph that you're not going to still understand what's happening with your graph. So that's when we're going to plot a few checkpoints, and the checkpoints are going to be inside your intercepts. After you do that, you should get a good idea what your graph looks like, put it together, make sure it's all one solid piece with smooth turns to it. And that should get you your graph. So let's look at this one. Sketch this particular graph. So I'm going to do step 1, LCT, leading coefficient test. So the x cubed is going to be the key to that. It's got a positive 1 in front of it and an x cubed, so a positive coefficient and an odd power. On the left, I should look like this, and on the right, I should look like that. So as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to positive infinity. Okay, so now I know what's happening on the ends of the graph. Step 2, intercepts. Okay, so if I want to do my intercepts, what do I have to do? I have to find my x-intercept. So I have to solve f of x equals 0. In that case, I have to solve x cubed minus 2x squared equals 0. Find the zeros. Well, it's a polynomial equation. How do you solve a polynomial equation? Primarily through factoring. So I'm going to pull out an x squared, and I'm left with x minus 2. So that gives me x equals 0 and x equals 2. These are my x-intercepts. Something to note is that this 0 here came from this factor. If you look, that factor occurred twice because of the power, so this is really what we consider to be a repeated 0. A repeated 0 is a 0 that occurs more than once. So this is a repeated 0. That's going to have some consequence with the graph, which we'll talk about in the future. But just start to look at it now and keep that in the back of your mind. This factor only occurred once, and this is a 0, so that wasn't repeated. Alright, so those are my x-intercepts. Y-intercepts. I have to find f of 0. So I plug 0 in for x. So 0 cubed minus 2 times 0 squared, 0. So my y-intercept is 0, my x-intercepts are 0 and 2. Alright, now that gets you a good idea of what the graph's going to, some things that go on with the graph. Now start putting it together. So if I look at my graph, x-axis, y-axis. So take a step back again. My x-intercept was 0 and 2. My y-intercept was 0. So 0 for x is my x-intercept. 2 for x is my other x-intercept. 0 for y. So these are the points I'm looking at. Also, leading coefficient test. Down on the left, up on the right. So down here, up here. Okay? Now, the idea is, alright, we have what happens on the ends of the graph, but we really don't have what happens in the middle of the graph. So that's where these checkpoints are going to have to come in. I know my graph goes through these 2 points right here, but I'm not sure what happens elsewhere. One thing I do know is that 2, this checkpoint right here, is the farthest to the right checkpoint, or x-intercept. And I know that on that end, my graph points up. So if this is my x-intercept, after that it's going to just keep going up. And this one's going to keep going down. Okay? Now, there are some other options, but that's largely what's going to happen with these. We still don't know what happens in the middle. Okay? So to determine what happens in this middle region here, what I have to do is plot some checkpoints. My general rule that I think you should follow when it comes to plotting checkpoints is pick one point between every 2 intercepts. So here's one intercept, here's another intercept, so I got to pick something in here. Pick whatever's easiest. I'm going to pick 1. Okay? So what I need to do is, if x equals 1, what does y equal? Well, how do I do that? Well, I have to find f of 1. Okay? If I find f of 1, that's going to tell me what y equals. Well, what was my function? My function was x cubed minus 2x squared. So I'm going to do 1 cubed minus 2 times 1 squared. And I get 1 minus 2, so negative 1. So that tells me when I plug 1 in, I get negative 1 as an answer. So this point right here is what my graph goes through. So to get from this point here to this point here, I have to go through this point. So my graph is going to do this. Now, that's not the perfect graph. My graph may not be exactly like that, in that this might not be the lowest point on the graph. Maybe my graph takes a little bit more of a turn downward, but I do know my graph does go through this point, and this point. And I also do know that on the end my graph points up, and on the SN my graph points down. So if I kind of smooth that all out now and sort of draw it as best I can from there, I get my graph. Okay? Now some of you might be saying, well, I could have easily got that graph simply by plugging this function, which was f of x equals x cubed minus 2x squared, into my graphing calculator. And you would be right. You could get the graph that way, but would you understand why the graph looks the way it does? would you understand how I could come up with this graph without looking at the calculator? And the answer is no. So you got to understand how these functions are working, and that's primarily what my goal is here, is to get you to understand how the function works, not just I hit a couple of buttons on my calculator and this is the picture I got, because then you really don't understand what you're working with. However, those are the steps that you're going to follow when you're trying to graph a polynomial function. So I take a step back again, follow these 4 steps, and you will be able to graph any polynomial function. I think your primary work is going to come in step 2. Sometimes finding that x-intercept, this process here, isn't going to be so easy, and we're going to spend some time looking at that a little bit closer. But if we can figure out how to do that all the time, basically how we're going to solve this equation regardless of how big or small the polynomial is, because factoring is not always going to be as simple as maybe the one we just did here, we'll be able to graph any polynomial using these steps. The leading coefficient test is never going to be that difficult. Look at the degree, look at the coefficient in front, you're done. Plotting checkpoints is just a matter of plugging numbers in. The y-intercept is finding f of 0. That's easy. It's this step right here, finding f of x equals 0, finding the zeros, that can get tricky. So we'll look at that a little bit closer.